Hey all, so hopefully you've already watched the video and done the lesson on second derivatives because we're going to keep going even higher. So we're still looking in 6.7. If you are stuck on any homework, please make sure that you're nominating it in the form so I can give you as much feedback as possible. Now, obviously, if it follows that there's a first derivative, there is a second derivative, there are third, fourth, etc. derivatives. So in terms of their notation, it's going to be just the same. You are always going to use the exact same rules, the product rule, the power rule, the quotient rule, all your trig rules. The notation, some for third, you'll still see 3 like this, or you'll see thirds in the powers like what we saw earlier. I realized I had a typo in the last one. The third power should be on the denominator variable, not on the d in the denominator. And then since like this is your third derivative. For the fourth one, they sort of stop writing all the hash marks because you could ask something for like the 13th derivative if you wanted to. And you don't want to write 13 apostrophes, so they just put a parentheses to show that it's a derivative and then whatever number they're looking for. So here, find the third derivative, that's what this tells us, of 1 over x minus 1. What I'm going to do in this case, and this is a nice trick that I want to show you, to find this third derivative, I'm going to rewrite my original function, which is 1 over x minus 1. I try to avoid the quotient rule whenever possible. So I'm going to rewrite this as x minus 1 to the negative 1. And I can use the chain rule here, but then the nice thing is that inner function is x minus 1. That means that g prime is just equal to 1. So when I multiply by 1, it doesn't actually do anything. So I'm just basically using, I can just use the power rule here. Bring it down in front, minus 1, which will give us f prime, which is negative 1, x minus 1 to the negative 2. You can write times 1 for the chain rule. It doesn't actually change anything, so that's just fine. Using the same logic, I am going to then use the power rule again to get my second derivative, and then that's negative 1 for the constant times negative 2, x minus 1 to the negative 3. Maybe do a little simplification here so that the constant is positive 2. X minus 1 to the negative third. We're asked for the third derivative. Right now we're at the second. So using the same rule again, power rule and chain rule, we get the third derivative, f triple prime as we might call it, as 2 times negative 3 x minus 1 to the negative 4. Which I would simplify to negative 6 x minus 1 to the negative 4. You can leave it like this, or that would be negative 6 in the numerator over x minus 1 to the positive 4 in the denominator. Either of these are fine, but it's just nice to be able to check against your answers in the back of the book. Now, why do we care about higher derivatives? It's just doing the same algebra skills. This is one of those things that actually has a really important scientific application, and that is with motion. So if any of you are in physics or you remember physics classes from earlier, when you talk about the motion of something, so here we're just going to talk about a particle like my little cursor here that's moving back and forth. The motion of a particle, it could be a car, it could be an object in flight, is modeled by the function s of t is equal to negative 4.8 t squared plus 12t, where s is measured in meters and t is measured in seconds. So what's important here is that this is what we call our position vector, or position function. So it's just our f of x. Velocity is, right, this is our position or our distance over time. Look, it's a fraction. This is, velocity is our first derivative. So if I want to ask for the velocity of something, all I need to do is find its derivative. If I want to find its acceleration, that's its second derivative. So if you're in a physics class, this is a really important set of ideas. position is the first derivative, position is the function, velocity is the first derivative, acceleration is the second. There's something called jerk, which is not used a lot in physics, but that would be the third derivative. Like, they keep having applications. So if I wanted to look here and I said, okay, well, if this is the motion of the particle, what is its velocity? Now, remember, velocity is related to speed in terms of just vocabulary. And the velocity function is just going to be your first derivative. So it's going to be s prime of t in the case, because these are the variables we're working with. So s prime here, we're going to use the power rule, negative 4.8 times 2t plus 12, which will simplify to negative 9.6t plus 12. And this is our velocity function, which you'll sometimes see also written, instead of s prime, you might just see v of t. They're interchangeable. So then for acceleration, remember this is going to be double prime of s. So we're going to use this function here, take its derivative. The derivative of negative 9.6t is negative 9.6. And the derivative of 12 is 0, so we are not going to include that. So then our acceleration function, a of t, is equal to negative 9.6. With these functions, we can then answer a lot of questions about this problem here. So for example, if it says, what is the initial velocity? Now, whenever you see the word initial like this in a problem, this means when t is equal to 0. That's all this means. So I'm using my velocity function, since it's asked for velocity, at t equals 0, which would be negative 9.6 times 0 plus 12. And so v of 0, the initial velocity, is 12. And often with these problems, we're going to include a unit, and that's why they tell us we're talking about meters and seconds. And since velocity is distance over time, this would be meters per second. Don't forget the units right there. Now here, we can say, oh, the acceleration when velocity is equal to 0. Now there's two ways to do this. One is you can find when velocity is equal to 0, so you can start with that question. Oh, when's velocity equal to 0? We'll say 0 is equal to negative 9.6t plus 12. You can do algebra, you can solve it, you can get t is 1.25. Plug that in. Oh wait, if you notice our velocity is our acceleration is a constant. So no matter what, that acceleration, even with all this solving here, our acceleration, no matter what that time is going to be negative 9.6 meters per second squared would be the unit on that. So we didn't have to do any algebra there, though it is good practice if you want. Let me know if you have questions about acceleration, velocity, or higher level derivatives.